Professor of Animal Science. It's my great honor on behalf of the Bauman Lecture Committee to welcome you to this lecture this afternoon. Before we start the program, I want to acknowledge the support from the Department of Animal Science, Food Science, and Division of Nutritional Sciences to join host this seminar. We also have a few people contribute to put the program together, including John Thompson, Alan Graffer, and also Chris here, and Aaron, and John from Food Science, and Marcel and Marty from Nutritional Sciences. Before the interview, I want to introduce Professor Butler from Animal Science to introduce the lecture to all of you. Please welcome him.
Good afternoon, everybody. What a great day. It's my great pleasure to start by introducing my friend and longtime colleague, Dr. Dale Bauman, for whom this lecture series is named. Dale, maybe you should at least stand up and say hello and be recognized. So this series came about, as you can see here, to recognize the remarkable career accomplishments and outstanding scientific contributions that Dale has made to several areas. Animal biology, food science, and nutritional biochemistry, as Shane said, in terms of who has pooled resources to make this happen. The primary research areas that Dale engaged in most actively, and there were a lot of other areas, but his primary research areas are listed here. Probably first and foremost, he's recognized for lactation biology, basically making milk, and through that he described and published a lot about the importance of bovine growth hormone to support that process. Regulation of metabolism and nutrient partitioning came along second. Then there was animal-derived functional foods, so you can see the cross-fostering across the fields. And then finally, toward the end of his most active career, before he retired, he was working on the environmental impact of animal production. So I'm an old farm boy, and I brought along with me a copy of Hoard's Dairyman. Probably not a lot of you young folks know about Hoard's Dairyman, but on the farm, this was next to the Bible. Okay. So anyway, Hoard's Dairyman did a special article in 2010, and I have some of the highlights here. But as you can see, maybe a little bit younger, Dale Bauman is portrayed in 1982 when he first published his research about the importance of growth hormone in terms of being able to stimulate cows to produce more milk, 10 to 40% more. And so that was the most noteworthy thing in 1982, noted by Hoard's Dairyman. When PST, Prozac, as it was known initially, was actually adopted and utilized by the dairy industry in 1993, one of our other colleagues, Bob Everett, did a study showing the progression and changes in milk production capability of dairy cows over the next 4 years after the adoption of the technology in cows that were treated with PST in yellow and the control group. So you can see a very marked effect on milk production. I continue to be astounded, I think actually scientifically astounded, at how important growth hormone is to the activity of the tissues in the lactating cow, but in all of us ourselves, same way. Not exactly the same way, but at least some of the same things. So first of all, the mammary gland. Basically, growth hormone increases the synthetic capacity and the ability to produce milk. The liver, very important in the dairy cow for producing glucose that's converted to lactose that underscores milk production. And then adipose tissue, which provides a reservoir or a reserve of energy through stored fat, nephas, non-esterified fatty acids in the blood, think of it as an energy source. Well, this led to, I'm not sure how to get rid of that thing up in the corner. Can we get rid of that little thing? It's going to bother the speaker too. That's a good idea. Thank you. Anyway, but what I'm trying to say here is that the metabolic effects of growth hormone across tissues leads also then to the ability to partition nutrients for different physiological activities. And Dale and one of our other colleagues, Bruce Curry, wrote an important review in 1980 talking about the partitioning of nutrients for pregnancy and lactation. And this turned out to be one of Dale's most highly, probably the most highly cited paper that Dale contributed over the years. And in that, they introduced the term homeoresis, which probably, again, maybe not all of you recognize. Homeostasis we hear a lot. Homeoresis we don't hear so much about, but physiologically it's really important because it describes the orchestrated changes for the priorities of a physiological state. And that's what's going on, as I say, in cows, but also in ourselves. As of this morning, that paper has 1,002 citations in Web of Science and 1,675 citations as counted up by Google Scholar. In 2006, I happened to see this paper where they looked at the agricultural sciences and they ranked the institutions by citations and citation impact. So you can see highlighted in red down there in the list, Cornell came out number 7 with 11,000 plus citations for that 10-year period. And Cornell University collectively then had the second highest impact of any other unit in the agricultural sciences worldwide. Just draw your attention to this new list. Dale Bauman, who's ranked number 2 for productivity and citations during that period, accounted for a little over 15% of the total Cornell citations during that important period to that high impact period. But 1,729 citations was just the tip of the iceberg, just the beginning. So as of this morning, once again, I've updated the citations list for credited to Dale, 19,000 plus citations in Web of Science, about twice that many listed as Google through Google Scholar. So he keeps going and going, and Journal of Dairy Science, August, he's got a paper in there. The last one I want to just highlight real quickly is the environmental impact. So in the left-hand graph, you see in green the average milk production from cows in certain parts of the world compared to their carbon footprint in blue down below. So the more productive cows have a small relative footprint compared to the cows in other parts of the world that have lower productivity and a higher carbon footprint. And basically, Dale and his colleagues over the years talked about how it's all about efficiency of production and how cows can use the same amount of maintenance energy, but then that gets redistributed and served by different cows for different levels of milk production. And today's cows are much more effective and efficient in producing milk, so they really have a lesser environmental impact. Well, as I mentioned, it keeps going on with Dale. We're just so pleased to have him here for the lecture, and we look forward to hearing Dr. Easter after he's introduced. Turn it over to whoever is next.
Well, thank you very much for that introduction to the Bauman Lecture Series, and it's my very great honor to be able to introduce the speaker for today's second Bauman Lecture, Robert A. Easter. Before I do, I want to remind all of you to please silence your phones. Bob Easter grew up on a farm in southwest Texas and earned his undergraduate and master's degrees in agriculture at Texas A&M and his doctorate in swine nutrition production at the University University of Illinois. He then joined the University of Illinois College of Agriculture faculty, where he taught swine production and nutrition courses. He directed the MS and PhD student research in swine nutrition, served as head of the Animal Sciences Department, the Dean of the College of Agriculture, the interim chancellor of the Urbana campus, and for the 3 years prior to his retirement in May of 2015, he was the president of the University of Illinois system. As an emeritus professor, he currently holds a part-time appointment in the National Center for Research and Professional Ethics. Professor Easter is a fellow of the American Society of Animal Science and an honorary member of the American Society of Agricultural and Biological Engineers. In 2008, President Bush appointed him as the chair of the Agricultural Advisory Board of the U.S. Agency for International Development. He serves on the boards of a number of non-governmental organizations and is an advisor to the ADM Institute for the Prevention of Post-Harvest Loss and to the USAID Soybean Innovation Laboratory. Please join me in welcoming Professor Easter.
I thank you for the opportunity to demonstrate my computational skill. When I received the email from Dr. Lay inviting me to come here, I really felt that I really wanted to do this, and for a variety of reasons. First of all, it truly is an honor to be involved in this lecture series, but also Dr. Bauman and I go back a good many years. In fact, as I was a PhD student at the University of Illinois, he co-taught the undergraduate animal nutrition course with my advisor, who also became a member of the National Academy. I had the privilege of TA that is a course, so I got to meet Dale, and certainly have followed his truly remarkable career since then. And it's truly an honor just to be here and a privilege to have a chance to visit with him. And last night, I think we bored the other table guests telling old stories about times in Illinois. And we both enjoyed it, so maybe that's okay. Well, my presentation today comes about in interesting ways in terms of being involved in this project, and I'll tell you a bit more about that in a few minutes. The topic of the presentation is a perspective on this report that was recently released by the National Academy of Sciences, looking at things that need to be done in agricultural research between now and 2030. And my grandchildren tell me that Grandpa, we were tired of hearing history, but I think it's relevant to spend just a minute of background. The land grant system of which Cornell was a part came about in the 1860s, actually approved by the U.S. Congress at the height of the American Civil War. And there were really three pressing needs during that period of time. The nation was beginning to develop industrially, and there were, if you have factories, if you have urban centers developing and supportive factories and people moving from the farm to the city, you need to have a system that produced more food than was being produced at that point in its history. So there was a priority given to agriculture. If you have industry evolving, you also need engineers to work in that industry. And incidentally, there was a civil war going on. So added to the Land Grant Act was the notion that reserve officer training would be part of the mandate. Agriculture and engineering in that era were national priorities, and they very much drove conversations in Washington. U.S. Department of Agriculture was also created the same period of time, and research in that organization began as a result of that. The Hatch Act was the second element that brought federal funding to end agricultural research at the university level. Hatch Act was passed in 1887, the date's wrong there. And it established a system of agricultural research universities, agricultural research stations across the country that were actually created under this act by state legislatures. And again, there's one here in New York. It required the state, first of all, to establish the stations. It provided federal matching funds by a formula based on population and agricultural productivity. So the state was obligated to create the experiment station and then to provide matching funds to the allocation from the Congress. And it was designed to encourage research to address issues relevant to the local agriculture in that individual state. And to the best of my knowledge, Dr. Bauman, it's the first example of the federal government engaging in a partnership with the states to fund research at universities. So this is kind of the history behind the Patch Act and the formula fund system that still exists until the current day. In fact, it's up for debate in the current conversation in Washington about renewal of the Farm Bill authorization. So all of us involved in wanting more research dollars are interested in seeing what takes place there. The next step in this process, and I think it's useful to think about, was led by an individual named Benny Bush, who had been Dean of Engineering at MIT, and during the Second World War led the federal research effort. And he was tasked late in President Roosevelt's era and then by Truman to develop a strategy for the national research enterprise following the conclusion of the Second World War. And Bush wrote a report, which was published, I think, in about 1946, that talked about how the U.S. should engage in research. New products, and it's some quote from there, do not appear full grown. They are founded on new principles and new concepts, which in turn are painstakingly developed by research in the purest realms of science. Universities will be the primary national research infrastructure, and obviously in that era there was focus on the Soviet Union and the potential threat that it was to the nation's security. So the notion was that the federal government would involve research universities very significantly in driving and supporting the national research effort. Other countries, particularly Europe, developed institutes apart from universities. And I think it's important that the U.S. system involved using universities as a primary platform for federally funded research. And that created the opportunity to blend graduate education with support for this kind of research. In short, if you read the report, the focus was on universities doing fundamental science, discovery research, which is a bit different from what universities in the experiment station were doing. That mission continues. But that industry would translate those discoveries, those new concepts, into some kind of application. The National Science Foundation came into existence as a result of it, and the mandate is here in 1950. And their priorities for the national research agenda increasingly were established at that point with the National Science Board. Grants were awarded competitively, which is a different model from what USDA had been mandated to do with formulas based on population and productivity of agriculture in the state. Health research has always been a priority. In fact, the best information I can find, there was created a marine research facility in 1790, so it's been part of the national agenda for a long time. The National Institute of Health came about in 1930. But it was in the late 60s and into the 70s that the National Institutes for Health began to increase and become as health became a national priority. And today, as you know, NIH is a major source of funding for university-based research. The other piece that I'll just add to this is a bit of a footnote. In the mid-1980s, for those of us who were around, there was great paranoia that Japan was going to be the technology leader in the world, and they were going to bring all the innovation into play and destroy the auto industry and a lot of other industries. The consequence of that, and I don't want to dwell on that because that didn't come to pass, the consequence was that in addition to doing research, there were a series of university research, there were a series of acts passed by the U.S. Congress and signed by the President during that era that obligated universities to engage increasingly in economic development and transfer technology, not just putting it in journals, but also actively involved in acquisition of patents and the commercialization or working with industry for the commercialization of technology. So the question came up in a conversation I was having earlier today about how about this relationship with industry and courts mandated by these statutes that were passed in the 1980s. So the question of the day that I want to come to is this one. Is there federal government providing sufficient funds for food and agricultural research? That's the question that was put before the National Academy Committee that worked on this topic. And more fundamentally, is there justification for assigning greater emphasis to food and agricultural research that is currently part of the federal portfolio? Obviously, if we're a recipient of those dollars, we think, sure, go for it, we need more. But the question that Congress would ask is, can you really justify putting taxpayer dollars that are very dear and can be used for very important activities in the food and agricultural research? And I would remind you of Parson Malthus, and many in the room will remember that Malthus was a vicar in the UK back in the late 1700s, who came up with this notion that population increases geometrically and that food production increases only arithmetically. Looking at it this way, you can see the line. And his hypothesis was that within a short period of time, and the world had about 1 million people at that point, we ran out of food. And so we had to do something about population growth. Well, the reality is that when Parson Malthus was putting his pen to paper, there was just about 1 million people on the planet. And in 1940, as the Second World War began to occur and the federal government got more involved in research, there was about 2.3. Today there's about 7.6. I would argue that Parson Malthus, in some sense, had one point right, and that is that when the world runs out of food, people starve, the population stops growing. The reality is that there's been incredible success in the food and agricultural system, and that's not just production, it's input, provision of inputs, it's the technology involved in production, harvesting, storage, transport, conversion of food products to human products and so forth, and delivery of those. But the reality is, somehow, through science, we have managed to stay up with population growth. And today, yes, there are people, and I'll show you a slide or two in a minute, who are food insufficient, but by and large, the world has continued to grow its food population. Well, looking to the future, and you've probably seen this and heard this story many times, but populations continue to grow. And most who project about population growth in this country and globally suggest that probably for another 30 years before population growth begins to reach a peak. That's speculative at best. And there were famines in our history. In the post-period of the early 1950s, if you had been living in places like India, the likelihood is that you would have been facing some very dire food situations. And science created the Green Revolution. And many of you know the story of the Green Revolution. It was an incredible increase in production. And there's a lot that we could talk about, what were the factors that was driving that. But it was truly research. And in many cases, in fact, almost, I won't say all, but very overwhelmingly, science done in U.S. laboratories and U.S. fields across the country that was a major contributor to the success of increasing food production. India today is a net importer of wheat, which is an amazing thing if you consider that. Well, the results were dramatic. Norman Borlaug gets a lot of credit for saving the lives of 1 million people. He was a plant breeder, but he was more than that. It was not only genetics of plants, he was also an advocate for changes in agronomic practices for irrigation, for fertilization, and different plantings and so forth. He received the Nobel Peace Prize in the late 1960s for that. And if you just look at wheat, which was Dr. Borlaug's specialty, look at 1950, the yield of wheat per hectare, and look at the dramatic increases that has taken place since then. The troubling piece, which I would point out here, is this apparent plateau. And if you look at most of these cereal products, and others may want to challenge me on this, I think you will see some change in that growth. Certainly we had a spurt 20 years ago, an increase in the slope caused by the introduction of genetically modified corn and soybeans. But the case for wheat is here, and there's a question about how much further we can go with GMO. Well, so I've given you more background than probably I should, but I thought it might be relevant to our conversation. Most of us weren't aware that there was a food crisis globally in 2008. We were focused on the financial crisis in that period of time. It was a wake-up call. The price of grains doubled, and if you were a crop producer in the Midwest, you enjoyed that. Oilseeds increased in price, There was a drought in Australia which impacted their wheat production. There was less production, drought in the Midwest and the states of the Great Plains where we produce most of our wheat. India became very anxious about their situation. They stopped exporting wheat. So if you were a family living somewhere in a developing country where you had $2 or $3 a day you used for your food budget, and you were basically buying grains and oil seeds as your primary food source, not processed things, but the fundamental grain, and the price of those ingredients went up by a factor of 100, then the likelihood is that you were facing a real challenge in terms of your food supply. And the consequence of this, I was chairing the USAID Ag Advisory Board during this period of time, and we talked a lot about this. And one of the consequences in areas where there was food insufficiency was civil unrest. And it gives you some sense of the stability. It's more than just about having enough food, it's about national stability, just because of the increases in price. These are about a year old out of the Economist. Now, one could argue that this issue in Africa is as much related to political upheaval as it is to agricultural productivity, but the reality is there are people in parts of the world, even today, who are struggling with famine. So, the question, who pays for agricultural research? Well, it's reckoned by the National Science Board that publishes this every couple of years, and I went on the website, tried to get the 2018 report, my apology. I couldn't download it, so I don't know what's in it. But in 2016, it was reckoned that about $3.3 billion was being invested in this country in agricultural research, about $1 billion in some way through federal resources, state and local governments by paying the salaries of faculty, by supporting research stations and so forth, was in about 800. Institutional funds, dollars that universities take out of their other general appropriation. Agribusiness, about 150 million. Not-for-profits, they're significant. The Gates Foundation, for example, has a $25 million grant on our campus currently to look at enhanced photosynthesis. But it gives you some sense, and the point I want to make is the importance of the federal support, but also the importance of the state support as well. And states are increasingly constrained in their ability to provide state support. Well, where does funding go, and what proportion of the federal appropriation is actually related to agriculture? Well, National Health and Human Services in 2012, again, my own data, is $55 billion, National Science Foundation 13, Defense Department, Department of Energy, and you notice at the very bottom, agriculture, $2.6 billion, about half of that for internal research, which is in USDA's Agricultural Research Service, about half of it goes to university-based research. It's a small amount, very small amount, compared to what's going to other places that support research. Now, one could argue that, yes, very correctly so, that work done in national science and NIH is also a part of agriculture, and I would certainly agree with that. There have been any number of entities, including the Association of Public and Integrated Universities, National CFAR, and a number of others, commodity organizations, who regularly make the trip to Washington and tell members of Congress you need to put more money in agricultural research, and the history is just not much success at all. And the typical response, and I made this trip year after year, was, well, what do you want to do? And so that brings us to the point of today's seminar. This is the report recently released by the National Academy of Science. And I think this is an introductory statement, and I would point out that the supporters of agricultural research, the Foundation for Food and Agriculture, are the primary financial supporters for this activity. I serve on the board of supporters of agricultural research, so my involvement in this has been from the perspective of one of the organizations that agreed to commit significant funding to this activity. I wasn't involved in developing the report, reviewing it, and other things, so I'm not an expert from that perspective. I'm pleased that the report came to pass. I listed the membership of the committee here, the two chairs, and it was a distinguished collection of a broad representation of different disciplines of science who engaged in a year-long activity that was, I had to do, because having read the report, a very serious conversation about these questions. And I very quickly point out, Dr. Scott sitting here in the room with us today, that he served on the co-chair of the review committee. He hastened to tell me he wasn't a reviewer, he just chaired the process, but I think he did much more than that, and I learned quite a bit today from my earlier conversations with him. So I want to say just a word about this organization called SOAR, Supporters of Ag Research. And it's an interesting story, and I think it's part of the American story. You recognize the logo of Ralston Marine. The family that owned that company was the Danforths, the second and third generation of Danforths. They sold Ralston Marine. There had always been a Danforth Foundation, but in the 1990s, they liquidated the assets of the Marine and dumped a very significant amount of money into the foundation, the family foundation. And as a result of that, decided to invest substantially in agricultural research. It was their history. They wanted to support it. The Danforth Plant Science Center in St. Louis is a lovely facility, about 150 scientists working there, postdocs, professionals, etc. It has a very nice endowment to support it. But Dr. Danforth, Bill Danforth, who I'll introduce in the next slide, became very conscious that there just wasn't much funding for agricultural research. He's an interesting guy. Bill was a medical doctor, a member of the family. His brother was a senator from Missouri. I got to know Bill in the early 2000s through involvement in advocating for agricultural research. And he had served for about 20 years as president of Washington University, a AAU research university. He had an appreciation for agricultural science, but also how you get things done in Washington. So he created this organization and asked a number of us to be on the board of the organization. There's a statement that he made here. And as a result of that, National Seed Farm, the Foundation for Food and Agricultural Research, you may recall, was created by the last Farm Bill, and they were given a large amount of money, but the obligation was that in order for them to support something financially, they had to have matching funds. So that's the basis for National Seed Farm becoming the other funder of this activity. So I want to talk just from a very superficial point of view about some of the findings from the report. Science breakthroughs to advance food and agricultural research by 2020. The major goal to improve the efficiency of the system, increase the sustainability of agriculture, which is something that concerns me, and increase the resiliency to changes, including things like climate change, etc. Those are all overarching goals. I don't think anyone would, these are very generic, I don't think we need to debate about these. Key research challenges, I'll just quickly go through these. Increase nutrient efficiency in crop production systems, reduce soil loss and degradation, mobilize genetic diversity for crop improvement, optimize water use. I don't know how much time you spend thinking about parts of the world where irrigation is a key function, India being one of those, and the extent to which the available water supplies, particularly groundwater, are being depleted. Folks, there's some places that are heavily dependent on irrigated crop agriculture that will run out of water in a few years, and that's something we need to be focused on. Improving animal genetics, food animal genetics, develop precision livestock production systems. One of my pet peeves, we talk a lot about crops. I'm an animal guy, as you heard in the introduction. I think we need to understand that a lot of what we grow as crops is fed to animals, and the opportunity to reduce that demand is by increasing animal efficiency. Dr. Bauman contributed to that, and that work needs to continue to go on. Early and rapid detection of diseases of plant and animals, foodborne pathogens. I make the comment in a number of settings that when I was a kid, most of the food that I ate came within probably 200 miles before I grew up. Today, the things that we have just in this break probably came, some of it, from halfway around the world. And we're all very happy to have strawberries year-round. We're all very happy to have blueberries year-round, but they don't grow in northern Illinois or in northern New York during the winter months. And last of all, reducing food loss and food wastage is a significant issue. I think one of the challenges that they grappled with is they were dealing with big problems, multidisciplinary problems in a world that is, by its very nature, science has become increasingly reductionist. We tend to focus within our discipline when there's a need also to focus more broadly and think about the whole of the production system. The early part of the report talks a great deal about this. We have to find solutions that are multidisciplinary, that trends that go across disciplines. They spoke of convergence, and I just want to, I like this term because the notion of bringing different disciplines, converging different areas of expertise around the solution of a problem. Approach to problem solving that cuts across disciplinary boundaries, integrates knowledge, tools, and ways of thinking from life and health science, physical, mathematical, computational science, engineering disciplines, and beyond to form a comprehensive synthetic framework for tackling scientific and societal challenges that interface with multiple fields. It's a lot of words, but the simple reality is we don't tend, I was successful when I was focused on very clearly defined problems as a scientist. Yet, how do you bring together disciplines? And I've had some wonderful conversations today, and I've been impressed with the extent to which this campus is focused on creating interdisciplinary initiatives and trying to bring multi-perspectives to the solution of problems. So, early on in the report, they talk about convergence. I can make that point. They want to challenge how do we define food and agriculture. It's not just growing crops, it's not just growing chickens and pigs, it's processing, it's inputs, it's the whole, if you will, the whole 9 yards. When I was involved in an initial challenge meeting that we had with the National Academy Charging Committee, and in that conversation we talked about moonshots. And we used this quotation that you're probably familiar with from John F. Kennedy's inauguration, or not inauguration, but later, when he said, we're going to go to the moon by the end of this decade. And in 1962, no one had an idea how we were going to get there. And I think our hope, at least from the SOAR organization's perspective, there will be some bold statements of that nature. We're going to eliminate the need for nitrogen fertilization by 2030. Now, that's a wild idea. I don't know how you get there, but that was the kind of thing Kennedy was saying, a moonshot. Well, what we got was science breakthroughs, and Norman, that's okay. I guess I'm going to hope for something a bit bolder. And I want to just quickly talk about the 5 breakthroughs, and then I'll wrap this up. Breakthrough 1, systems approach, which you'd expect with the conversation about convergence. And the systems approach, they recommend that funders focus on transdisciplinary science and systems that to be prioritized as we think about agriculture's most vexing problems. So the structure of this, a breakthrough, we need to do systems, what should be done, create more priority in terms of funding around those kinds of approaches to problem solving. Breakthrough number 2, the development of and validation of precise, accurate, field-deployable sensors and biosensors that will enable rapid detection and monitoring with capabilities across various food and ag disciplines. I'm an old guy, and so maybe I'm just carried away with some of the things going on. I think digital agriculture is a fascinating opportunity, and that speaks to that recommendation. Create initiatives to more effectively employ these technologies in all areas of food and agriculture. Breakthrough number 3, application of integrated data science and software tool systems. And it talks about in managing the food and agricultural system. Maybe part of the reason because I was on the board of a startup company and had a very successful exit recently was dealing with predictive analytics, and so that gave me a chance to see the value of doing some of these things. Establish initiatives to nurture emerging area of agri-food informatics and the developing adoption of all information technology, data science, artificial intelligence, food and agricultural research. And I'm delighted this morning to have conversations around the multi-college initiatives that's going on in this arena on this particular thing. Break number 4 relates to genomics and the use of agricultural gene technologies around editing agricultural imported organisms. And I think that's something that we would probably see as something that should be there. And it talks about an initiative to exploit the use of genomics and precision breeding to genetically improve crops, animals, etc. And the last is also an interesting, and I'm pleased it was in there, this whole issue of the genome and how relevant it is. It's not just, I think of the genome as being anaerobic microbiology, the intestine, but the reality is the soils are huge complex of microorganisms, and we know very little about their function and how they sustain the productivity of our soils and contribute to plant production. And so it talks about establishing an initiative in animal soil and microbiomes and their implications for the food system. Well, so they spoke then to specific areas around 7 different areas: disciplines: crops, animals, food science, soils, water, data science, and the systems approach. So there's a chapter in some detail that talks about each of these. And they made recommendations, and I'll just give one example, the one that was in animal agriculture. They mentioned a few things: disease detection, management using data-driven approaches, genetic improvement, as we spoke about, increasing efficiency of not only livestock, poultry, but also agriculture, and then objective sustainability. And I think all of us would understand that animal well-being, animal sustainability is part of the conversation, and it's something that we have to give attention to, not just because of public concern, but also because of the productivity of animals that are in good health, that are well cared for, is better than otherwise. Further considerations, and this is the last slide, they report, and I was pleased to see this, acknowledge that it's just about funding individual or group or multidisciplinary teams research, but it's also providing those individuals with the tools, the infrastructure, facilities, and human capital necessary to do this cutting-edge research. USDA historically has not been particularly abundant in its funding for some of these things, so I was glad to see that there. They did acknowledge the importance of the experiment station system nationwide, and also cooperative extension services and delivery vehicle. I would quickly comment that the nature of extension is changing rapidly. The needs for extension are changing rapidly. And I think it's up to the challenge of those who are managing the extension systems to understand and determine what their future mission is. It also makes the point, which is what we all hope for, that public and private funding for agricultural research is inadequate to address critical needs. And also another point that I think is particularly important: efforts to renew interest in food and agriculture, to engage non-agricultural professionals, excite the next generation of students. My generation of people working in colleges of agriculture, primarily we came from the farm. And as agriculture became more efficient, Dad said, "Don't come back here, I've got another brother that can take this place over for you, find a job somewhere else." So a fair share of us wound up working in universities, and we brought that background and that understanding with us. The next generation of agricultural scientists and people who do the professional business of agriculture, they may be traders on the Chicago Board of Trade, they may be working in the food industry, are not going to come to the farm. Kids aren't there. They're going to have to come out of urban settings. And the challenge is, how do we excite those young people about possible careers? And more importantly, how do we adapt the undergraduate curriculum, particularly given the kind of preparation that we need? I have taught in the swine production course at the University of Illinois since 1976. And what we teach in that course hasn't changed remarkably throughout. I just give the history lecture these days. I was getting a physical look there. That course needs to be revamped. And a lot of the undergraduate courses that teach students who come with different backgrounds need to be given some thought. Well, a better understanding, and this is the last point, of the linkage between physical and the social economic sciences. We've talked about this 2 or 3 times today. How do we increase the consumer's understanding of the food system, the sense of comfort with the safety of the system as it exists today, legitimately the sense of the value of the science that's used in modern food production systems. Those are issues that we also need to give some attention to. With that, I will wrap. And Dr. Bailey, we have a few minutes for questions or not.
So we do have a few minutes for questions. Is there questions? So I'll take the moderator's priority here. In nutrition, there's a lot of interest in precision nutrition. And as I listen to you, it occurs that maybe precision nutrition and precision agriculture ought to be coming up together. Is that something that can be considered in your thoughts?
You know, I'm impressed with what the crop sciences have been able to do, at least in my part of the world, with what they call precision agriculture, prescription agriculture, where fertilization is adjusted moment by moment across the field. Planting is adjusted to the pressure applied upon seed and so forth. It's amazing what's out there. I'm frustrated that we in the animal industry haven't done more in that area, and I think the same would apply to some of the human opportunities. I guess my challenge is I don't want some computer telling me what I should eat every day. My wife already does that. But the reality is, it's probably help us.
Hi, thank you. I wrote down my question so I don't mess it up. So we in developed countries are moving away from livestock meat in general as a trend in our diets for its environmental and health concerns as well as issues of ethics and animal well-being. Yet this report seems to take a large focus on improving the growth and intensification of the livestock industry, and it sort of takes that as a given. So what do you see as the future balance between declining meat consumption in industrialized countries and increased demand for meat in rapidly developing countries such as India and China, where the technologies that can ameliorate the environmental and ethical concerns that we have in developed countries might not be economically feasible or prioritized in those developing countries?
You've said a lot. We had this conversation earlier today. I think one of the disappointments that I share with Dr. Scott is there was no commentary relative to alternative protein sources. And so that, and I guess the second comment I would make is that when I give talks to Illinois corn and soybean farmers, I talk about the fact that, I'm not very honest, I guess, I talk about the fact that globally meat consumption, food, animal protein consumption is growing about 2% per year, and that's been going on for 20 or 30 years. And they get excited because it's a working for corn and soybeans. But the reality is there's probably some point in which if that growth, if affluence in developing countries continues to grow, the capacity to diversify the daily diet continues to grow, there's some point at which I don't think we can actually achieve sustainably the amount of food, those products that we produce. 2 weeks ago, I really retired to give advice to people. I wrote to the head of our animal sciences department and suggested that he might want to think within the meat science group of hiring someone for a faculty vacancy that works in the area of alternative protein sources. That's heresy for an animal scientist to say that. But I think the final point you made, and I've spent a fair bit of my career working in developing parts of the world, particularly as it relates to swine production. And the challenge in transitioning from very traditional systems, which are not necessarily environmentally friendly, to larger systems, are very significant in doing it in ways that are, what I would argue, environmentally sustainable, and don't overuse water supply, don't contaminate water supplies, and so forth. The alternative, and I'm not negative in the sense, the capacity to build integrated systems, and we talked about this as well today, that take full advantage of those other products, particularly waste coming out of those, to generate energy, to recover the nitrogen and phosphorus used back in fertilization. Science is finding ways to do that. So there are ways of addressing some of these concerns. The challenge for a limited resource environment is how do you apply those techniques.
Any others?
So what happens next? How do you, this is going to require some big time changes in how the government funds things and current requirements and changes in the university operations, how some of those monies are handled. What happens next to get this really rolling?
You know, we live in a world that's very decentralized. My hope, and I would think that that's more broadly the hope of those who are involved, is that this report gets attention by decision makers within universities and experiment stations as they think about the faculty of the future, the programs that perhaps need to be launched off into the sunset, and other new areas that need to be developed and expanded within not just the research portfolio, but the curriculum. It's cited, and I was pleased to see that in the report. Our crop sciences department now has a joint degree with computer science, which I think is relevant to some of the things that are in this report. I think the bigger challenge is in Washington, and obviously a number of these organizations that I mentioned earlier as being advocates will hopefully use this as they advocate for increased funding. In times when I don't want to go into a great discussion about the appropriations process, but there's a lot of hands at the table when agricultural appropriations are done. And research is sometimes a difficult one to sell because it's easy to demonstrate immediate impact with some things that are sometimes harder to demonstrate in research. The long-term impact, on the other hand, can be very great. But convincing somebody who's up for election the next year to support that is a challenge.
Okay, so we'll introduce Dr. Bauman and thank Dr. Easter one more time.
We didn't practice this, so. It's my pleasure to present this plaque to you in honor of your wonderful lecture. Now I see the program says for me to say a few words. I don't really have words to say. What a wonderful lecture, and there are very few people that have the breadth of areas to be able to show us, present a lecture to show us the broad picture in producing food for agriculture, and so I really appreciate it. A couple things that back what seems like a long time ago, I was for 7 years on the board of agriculture for the National Sciences, National Academy of Sciences, and chairman for a few years. And so one of the things we realized in research that I remind you young scientists is that funds for research really represent public money for public good. And I think we always have to remember that as we explain to people less familiar with science why it's good to support research. The second thing I thought of is we face some interesting challenges because this is the time when the public is really quite skeptical of science. And so it's a big challenge for us to explain science to the public. And when we have shows like Dr. Oz telling people what nutrition is all about, we know we have big time problems. And so that's something we have to deal with. I did about several years ago, I was interviewed by Newsweek magazine. I did a calculation for them using the curve that Dr. Easter presented of the population growth. And you can calculate the amount of food needed for the next 50 years for humankind is equal to the amount of food previously produced in the history of humankind. The area under the curve to the present time, and that population is about equal to what it will be over the next 50 years. That's an amazing thing to keep in mind as we move forward. I can't think of, how do I end this, Shannon? Well, we thank you very much, and we thank all of you for coming to this lecture.
So the seminar is closed. Thank you very much for attending.